Solving mixture problems using separable differential equations. A mixture problem tracks how the amount of a substance, like salt, dye, medicine, etc., changes in a well-mixed system over time. We let y of t represent the amount of the substance, for example, kilograms of salt, in the tank at time t. The rate of change of y of t is, in general, dy dt is equal to the input rate minus the output rate. Let's look at our first example. Here we're told that a tank initially contains 10 liters of water and 0 kilograms of salt. So in other words, there's just pure water in the tank initially. A brine, which is salt dissolved in water, with a concentration of salt of zero point 0.1 kilograms per liter, flows into the tank at a rate of 6 liters per minute. The mixture is kept uniform by stirring and flows out of the tank at the same rate, 6 liters per minute. Let Y be the amount of salt in the tank at time t. For this first example, we're really going to break this down into steps. So for part A, at what rate does salt enter the tank? Well, the way that salt enters the tank is through this brine, this salt dissolved in water, which has a concentration of zero point 0.1 kilograms per liter. So I'm going to start with that. I'm going to have zero point 0.1 kilograms per liter. This is, again, the concentration of brine. All right, well, this brine is flowing in at a rate of 6 liters per minute. So if I multiply the concentration of brine times the rate at which this brine is pouring in, 6 liters per minute, let's take a look at the units. The units of liters is going to cancel out. So again, we multiplied by the rate at which the brine pours in. And so the units that we have left over are kilograms per minute. And the value that we have is 0.1 times 6. So we have 0.6 kilograms per minute as the rate at which salt enters the tank. Salt is measured in kilograms and it's happening per minute. So we're multiplying the concentration of the brine, that's the amount of salt in every liter, times the amount of liters that come in per minute, and that gives us how much salt is pouring in kilograms per minute. This is the entering rate. For part B, we're being asked at what rate does salt leave the tank? So let's think about what's happening here. We have pure water and we're putting in this salt water mixture and it's being mixed around, and then that new mixture is leaving at a rate of 6 liters per minute. So we want to know how much salt is in that mixture. Well, Y is the amount of salt at any time t. So we need to figure out what's the concentration of the salt at any given time. Well, the amount of salt is Y, and so the concentration is going to be Y over how much liquid is in the tank. Well, the amount of liquid in the tank is always going to be 10 liters because it starts with 10 liters of water, and then this salt water is coming in at 6 liters per minute, and then it gets mixed around, and then that same amount, 6 liters per minute, is leaving. So at any given time, there's still only going to be 10 liters of water. So the concentration is Y over 10. So we're basically doing part to whole. So Y kilograms per 10 liters. So this is the concentration of the mixture. And we need to multiply that by the rate at which that mixture is leaving. So that rate at which the mixture is leaving is 6 liters per minute. So this is the rate of mixture leaving. So here, I'm going to just go ahead and cancel the liters again. And we're going to end up with 6y over 10 kilograms per minute. And we can reduce that down to 3/5 y kilograms per minute. For part C, I want to set up the initial value problem to find the amount of salt y in the tank at time t. So an initial value problem is a differential equation with an initial condition. Our differential equation, we said that for a mixture problem in general, dy dt is equal to the input rate minus the output rate. Well, we just calculated that the input rate was 0.6 kilograms per minute, and the output rate was 3/5 y kilograms per minute. Well, let's go ahead and recognize that zero point 0.6 as a fraction is 3/5. So what we have here is dy dt is equal to 3/5 minus 3/5 y with units that are the same, kilograms per minute. This is the rate of change of y, the amount of salt, with respect to time. And we can factor out a 3/5. So dy dt is equal to 3/5 times 1 minus y kilograms per minute. So here is my differential equation, and it's missing an initial condition to be an initial value problem. The initial condition has to be on the amount of salt initially. Well, the tank initially contained 0 kilograms of salt. It was just pure water. So here's my differential equation, and my initial condition on y, the amount of salt, is that at time 0, the amount of salt equals 0 kilograms. So here is my initial value problem. And now part D is really the big part. Let's solve the initial value problem to find the amount of salt y in the tank at time t. So notice that my initial value problem is a separable differential equation. I can go ahead and divide by 1 minus y over here. So I would get dy over 1 minus y is equal to, I'll leave the 3/5 over here, 3/5 dt. So now I can go ahead and integrate both sides. And here I'm going to get a natural log, but there's 1 minus y, so we will have a negative in front. So negative natural log, the absolute value of 1 minus y, is equal to 3/5 t plus c. Now let's go ahead and take a moment to solve our initial condition, using our initial condition. So here, if I use my y of 0 equals 0 initial condition, we substitute this 0 into t and this output into y, and we end up with negative natural log of 1 is equal to 3/5 times 0 plus c. Well, natural log of 1 is 0, so I end up with just c is equal to 0. So I have negative natural log of 1 minus y is equal to 3/5 t. Now I'm going to go ahead and multiply by the negative. So natural log absolute value of 1 minus y is equal to negative 3/5 t, and we'll make some space. From here, to solve for y, I'm going to exponentiate both sides. So if I have e to the natural log of absolute value of 1 minus y, e to the negative 3/5 t, now e and natural log cancel, so absolute value of 1 minus y is equal to e to the negative 3/5 t. Now right here, I have absolute value of 1 minus y, and I can't just drop the absolute value bars without an understanding of the quantity 1 minus y. And to get that understanding, I'm going to refer us back to the original differential equation. So dy dt was equal to 3/5 times the quantity 1 minus y. So what this represents in the context of the problem is this is the rate of change of salt in the tank. Well, what do we know about the amount of salt in the tank? Y. Y is increasing. Y is the amount of salt, and salt is increasing. I mean, how do I know that? Let's think about it. I have this tank full of pure water, and I'm adding salt water to it, and I just keep adding salt water to it. So salt is increasing. If y is increasing here, then we know that the derivative, the rate of change, had to be positive. And well, 3/5 is already a positive number, so this quantity here, 1 minus y, must be positive. So here, I can go ahead and drop the absolute value bars because I know that 1 minus y is a positive quantity. So since 1 minus y is positive, I can just drop those absolute value bars, and get e to the negative 3/5 t. The other possibility, if for whatever reason salt was decreasing, then we would drop the absolute value bars, but then we'd have to put a negative in front of that quantity because, again, the amount of salt would have been decreasing. But here, since the amount of salt is increasing, y, dy dt had to have been positive. So 1 minus y would have had to have been greater than 0. So we can just simply remove those absolute value bars here. And now we can go ahead and solve explicitly for y as a function of t. So we get negative y is equal to e to the negative 3/5 t minus 1. And then let's divide the negative through. So we get y is equal to, I'll write this as 1 minus e to the negative 3/5 t. So this is the solution to my differential equation. This represents the amount of salt at any given time t. So this should work for our initial condition. If I substitute in 0, I should get out 0. Well, if I let t equal 0, e to the 0 is 1, and 1 minus 1 is 0. So that worked out. My initial condition works, and now this function represents the amount of salt at different times t. Now for part E, find the amount of salt in the tank 10 minutes after the process starts. Well, we just found the solution, y equals 1 minus e to the negative 3/5 t. This is the amount of salt at any time. Well, after 10 minutes, we can find the amount of salt if we just substitute in 10. So y of 10 is what this question is asking me for. 1 minus e to the negative 3/5 times 10. So here, 5 goes into 10 2 times, so this up here is going to end up being negative 6. So we have 1 minus e to the negative 6. And so if we substitute that into a calculator, we're going to get approximately 0.9976. And what are the units? Well, this is an amount of salt, and we measured our salt in kilograms. So approximately this much salt in kilograms is in the tank after 10 minutes. For part F, we're asked to find the concentration of salt after 10 minutes. So for concentration, we're looking for a part to a whole. Well, after 10 minutes, how much salt is in there in kilograms? We just calculated that to be y of 10, so y of 10 kilograms. And then the whole, how much liquid is there throughout the course of this mixture problem? There's always going to be 10 liters. So the total concentration, y of 10, that was 1 minus e to the negative 6 over 10. So if I approximate that, it's going to be 0.0998 kilograms per liter. That's the concentration of salt after 10 minutes. And finally, part G, when will the concentration of salt in the tank reach 0.05 kilograms per liter? So in general, the concentration, the part to whole, is going to be the formula for y, 1 minus e to the negative 3/5 t over 10. So that's going to be my part to whole. This is in kilograms and this is in liters, right? So this is kilograms, this is in liters. When is this going to equal 0.05 kilogram per liter? So I'm solving for t, right? The question is asking me for a time. When is this going to happen? So I'm trying to solve this equation here. So I'm going to go ahead and erase the units just to not complicate things here in my solving process. So to solve for t, I'm going to go ahead and multiply by 10. So I'm going to have 1 minus e to the negative 3/5 t is equal to 0.5. If I multiply by 10, I'm just going to move the decimal over. And then I'm going to go ahead and, let's see, I'm going to subtract 0.5 to the left and add e to the negative 3/5 t to the right. So 1 minus 0.5, that's 0.5. So I'm going to have 0.5 is equal to positive e to the negative 3/5 t. And then to solve for t, I'm going to take the natural log of both sides. So natural log of 0.5 is equal to negative 3/5 t, because remember, natural log and e will cancel and we'll just get what's up in the exponent. And then I'm going to multiply by negative 5/3 on both sides. So negative 5/3 natural log of 0.5 is equal to t. So that's the exact value. Let's go ahead and substitute it into a calculator to approximate this time. It's about 1.16 minutes. So it only takes about 1.16 minutes in order for the concentration of salt in the tank to reach 0.05 kilograms per liter. We just walked through an example, but here is a general mixture problem setup. A tank initially contains a liquid of volume V0 mixed with an initial amount Y0 of another substance. A mixture with concentration S is pouring into the tank at a rate of R. The tank has an open drain, so the well-mixed solution immediately drains out of the tank at the same rate the liquid flows in, R. The rate of change of the amount of added substance Y at time t is modeled by the following initial value problem. We have dy dt equals SR. So S is the concentration, and then R is the rate at which that is pouring in, minus, this is the output rate. Y over V naught is the concentration of the well-mixed solution times the rate at which the well-mixed solution is leaving. And the initial condition, Y of 0 equals Y naught. Let's go ahead and look at another example. A 200-gallon tank is half full of distilled water. At time t equals 0, a solution containing 0.5 pounds per gallon of sugar enters the tank at a rate of 5 gallons per minute, and the well-stirred mixture is withdrawn at the rate of 5 gallons per minute. Part A, how much sugar will be in the tank after 20 minutes? So this is not as guided of a problem. So we're going to have to kind of fill in all of those pieces. So let's go ahead and start by saying, let Y be the amount of sugar at time t. We're being asked how much sugar will be in the tank after 20 minutes. So what we want is Y of 20. That's what we're being asked for. Now, in order to find Y, we're going to solve this initial value problem that we have to set up. So we're going to have to set up our differential equation, dy dt, which is going to be the input rate minus the output rate. The input rate is going to be the concentration times the rate at which that liquid enters. So the concentration is 0.5. We're going to have 0.5 pounds per gallon times the rate at which it enters, 5 gallons per minute. So notice here that gallons cancels, minus the rate at which it exits. Well, here, Y is the amount of sugar at time t. So we're going to have Y over the volume in gallons. So here, this 200-gallon tank is only half full of water. So if it's only half full of water, there's only 100 gallons in the tank. So the initial volume there is 100. So we have our concentration, Y in pounds per 100 gallons, and then times the rate at which it's leaving, that 5 gallons per minute. And again, gallons cancels. So what we have here is 2.5 and then pounds per minute minus 5 over 100, that's Y over 20, and then again, pounds per minute. And so this is dy dt, and we'll simplify it a bit and remove the units in a second. And then my initial condition, how much sugar is there to begin with? Y of 0. Well, this is filled with just distilled water, and distilled water doesn't have any sugar in it to begin with. So Y of 0 is equal to 0. All right, so now let's go ahead and clean up this differential equation to solve. How about we write 2.5 as a fraction? So this is 5 over 2, and then minus Y over 20, right? And this is dy dt. And again, this is in pounds per minute. We'll drop the units in a second. So here, this is a Y. Let's go ahead and write this to have common denominators. So we'll multiply the top and bottom by 10 here. So this is going to be 50 over 20. So we have dy dt is equal to 50 minus y over 20. Let's make a bit of space to solve. All right, so here I'm going to go ahead and divide 50 minus y over here under dy. So I'm going to have dy over 50 minus y is equal to, I would have 1 over 20 left over, and then I'm going to multiply by dt. So we've separated the variables here, and then we'll integrate both sides. Now we could have multiplied the 20. The constant multiple can kind of go to either side. So I'm going to leave it over here, 1 over 20. So here the integral of 1 over 50 minus y is going to be negative, because of the negative 1 in front of the y. Negative natural log absolute value of 50 minus y is equal to 1 over 20 t plus c. And then we'll go ahead and use our initial condition. So our initial condition, y of 0 equals 0, will allow us to solve for c. So we'll have negative natural log of 50, and then equals just 0 plus c. So really just negative natural log of 50. 50 is already positive, so we don't need those absolute value bars. So this is our value of c, negative natural log of 50. Let's plug that back in. Negative natural log of 50 minus y is equal to, I'm going to write this as t over 20 minus natural log of 50. And we're going to go ahead and try to solve for y now. So I'm going to multiply the negative to the other side, or divide by negative 1. Natural log absolute value of 50 minus y is equal to negative t over 20 plus natural log of 50. And then I'm going to exponentiate both sides here. So we're going to make e the base of both sides, and e to the natural log cancels. So we have absolute value of 50 minus y is equal to, now on this side, what I'm going to do is write this as e to the negative t over 20 times e to the natural log of 50. So here I'm taking e to the first part of the exponent, and then times e to the second part of the exponent, because remember, we can put these back together with the same base if we add those exponents. So I'm taking it apart because e to the natural log right here would cancel. So we can't cancel it up here because there's these two terms up in the exponent, but here I can. And so we need some more space. We have absolute value of 50 minus y so far is equal to 50 e to the negative t over 20. And then what we have to do is basically decide what is going to happen with this left-hand part, because it has the absolute value bars around it. So I take a second to remind us about the differential equation, dy dt, the rate of change of sugar, that was equal to 50 minus y over 20. dy dt was 50 minus y over 20. And what did we know about y? Y, the amount of sugar, is increasing, because again, we're pouring this solution that has sugar into a tank that's pure water. So the amount of sugar is increasing. So dy dt must be positive, right? So that means that 50 minus y, this quantity must be positive, because the bottom 20, that's already positive. So 50 minus y must be positive, right? So 50 minus y must be greater than 0. So we can go ahead and drop the absolute value bars and say 50 minus y is equal to 50e to the negative t over 20, and then solve for y. What I'm going to do is I'm going to add the y to the right side and subtract 50e to the negative t over 20. So I have 50 minus 50e to the negative t over 20 is equal to y. So this represents the amount of sugar at any time t. We want to just do a quick check on our initial condition. If I substitute in 0 in for t, e to the 0 is 1, so I'd get 50 minus 50 is 0, and yeah, there's 0 kilograms of sugar, or pounds of sugar in this example, initially, right? So that checks out. This is, well, I guess I don't want to box it in. This is the amount of sugar at any time t. What did we want the amount of sugar after 20 minutes. So we want y of 20. So 50 minus 50e to the negative 20 over 20. Well, that's nice, right? So 50 minus 50e to the negative 1. And if we substitute that into a calculator, we get approximately 31.6 pounds of sugar after 20 minutes. For part B, what is the concentration of sugar in the tank after 20 minutes? So here we want that part to whole situation happening. So the amount of sugar in the tank after 20 minutes was 50 minus 50e to the negative 1. And then the amount of total volume was 100 gallons, right? So this is going to be pounds per gallon. And if I substitute it into a calculator again and approximate, it's 0.316 pounds per gallon. That is the concentration after 20 minutes. Before moving on, I'm going to return to part A and give us an alternative way to solve that doesn't involve needing to think about the whole absolute value of 50 minus y thing. So what I'm going to do is erase all of the work after evaluating the integral. So I'm not going to solve for c right away. So we evaluate the integral, and then instead of solving for c immediately, I'm going to move forward with trying to isolate y. So I'm going to go ahead and get the natural log by itself. So I'm going to multiply through by the negative, and that's going to give me natural log of absolute value of 50 minus y is equal to negative, I'm going to write this as t over 20, minus c. And then I'm going to exponentiate both sides. So e to the natural log of the absolute value of 50 minus y is equal to e to the negative t over 20 minus c. And now e to the natural log, those are inverses. So I have absolute value of 50 minus y is equal to e to the negative t over 20 times e to the negative c. So here I'm using the properties of exponents, so I can split this up to be e to the negative t over 20 times e, that same base, to the negative c. But e to the negative c, I mean, that's just some constant, right? And because that constant is still there, we can let it absorb the plus or minus that's sort of coming from this absolute value of 50 minus y. So absolute value of 50 minus y, that quantity can either be positive or negative because of the absolute value bars around it. But this generic constant here can also be a positive or a negative. We haven't solved for it yet. So basically what we can do is we can remove the absolute value bars here, and it just becomes 50 minus y. And then this e to the negative c, it's some other constant. Let's just call it c1. And then we still have c1 times e to the negative t over 20. So we've eliminated the absolute value bar problem, and we have not yet solved for c though, right? So that's kind of the difference, is that we can now go ahead and solve for this other c1. It's going to be a different c value than if you obviously solved for it initially, but it's still going to give us the same final answer. I'll go ahead and right now solve for c1. So we know the initial condition was y of 0 is equal to 0. So 50 minus 0 is equal to c1 e to the 0. And so I end up with just 50 is equal to c1. So I have 50 minus y is equal to 50 e to the negative t over 20. And then to solve for y, I can just add the y and subtract this whole quantity here. So it's going to leave me with a final answer of 50 minus 50 e to the negative t over 20. And that was the exact same answer that we got before. But we did not have to handle the absolute value because we allowed that plus or minus to be absorbed by the constant that's still here because we didn't solve for it right away. So that's another way that we could handle the work on this type of problem. In this example, we're told the air in a room with volume 180 meters cubed contains 0.15% carbon dioxide initially. Fresh air with only 0.05% carbon dioxide flows into the room at a rate of 2 meters cubed per minute, and the mixed air flows out at the same rate. Find the percentage of carbon dioxide in the room as a function of time. What happens in the long run? We're going to go ahead and start by letting y equal the percent of carbon dioxide in the room, because that's what we're trying to find. Find the percentage of carbon dioxide in the room at any given time. But this is going to change things a bit, and we'll see how in a second. So we'll start our setup of our initial value problem. The differential equation is going to be dy dt, and we want to multiply the concentration rate times the rate at which the air flows into the room. So if we're going to keep y as a percentage, we'll go ahead and keep 0.05 as a percentage, but you're going to see in a second how we have to do a little modification. So here, if I keep 0.05% times the rate at which that flows in, that's 2 meters cubed per minute. And then we're going to have minus the rate at which the carbon dioxide leaves. So y, again, is the percent of carbon dioxide over the volume of the air in the room. That's 180 meters cubed. And then the rate at which it flows out is also 2 meters cubed because it flows out at the same rate. So 2 meters cubed per minute. So if we notice in our rate of leaving, our meters cubed is going to cancel. But over here in our rate of entering, it's not. And that's because if we keep 0.05% as the carbon dioxide, then to get the concentration, we do have to divide by 180 meters cubed, and then they cancel. So the alternative would have been to change 0.05% into a decimal to drop the percentage. But then later we would have had to convert it back to a percentage by dividing by the volume anyway. So there's just a couple of different options, but if we're going to keep y as the percent, and that's what we're trying to find, then we just have to be careful here, and units really help us out. So now I'm going to go ahead and clean this up a bit. Here I have 2 over 180. Here I have 2 over 180, and that simplifies to just 1 over 90. So I'm going to go ahead and leave it like this. I'm going to put 0.05 over 90, and then minus y over 90. And then the units here, I mean, are kind of weird, but it's going to be percent per minute. So here is our differential equation. We need our initial condition. So initially at time 0, what is the percent of carbon dioxide in the room? So we get to keep this as is. It's a percentage, and here when we solve this differential equation for y, we will get a percent. So here y of 0 we can keep as 0.15%. Okay, so now between these two, I can factor out a 1 over 90. So I have 1 over 90, and then 0.05 minus y is equal to dy dt. So I can do this so I can separate the variables. I'm going to divide by 0.05 minus y over here. So dy is 0.05 minus y equals 1 over 90 dt. And we'll need some space to solve this. All right, so if we integrate both sides here, we're going to have negative the natural log absolute value, 0.05 minus y is equal to 1 over 90t, or t over 90 plus c. Now we'll go ahead and use our initial condition, y of 0 equals 0.15. So 0.15 is the output value, and then 0 is the input value, which is t. So we're going to have negative natural log of 0.05 minus 0.15 is equal to 0 over 90 plus c. So we get negative natural log of the absolute value of negative 0.1 here is equal to c. Well, the absolute value of a negative makes it positive. So we just have negative natural log of 0.1 is equal to c. So we can go ahead and substitute that back in over here. So negative natural log, absolute value 0.05 minus y equals t over 90 minus natural log of 0.1. And then we'll go ahead and multiply through by the negative. So we get natural log 0.05 minus y equals negative t over 90 plus natural log of 0.1. We will exponentiate both sides here, and we'll make e the base of both sides so that e and natural log will cancel, and we need more space. All right, so now we have absolute value of 0.05 minus y is equal to, okay, so hopefully you can kind of stay with me on this. We would write this as e to the negative t over 90 times e to the natural log of 0.01, and e and natural log will cancel. So what we're going to get is 0.1 in the front times e to the negative t over 90. All right, and now we have the absolute value bars around this 0.05 minus y quantity, and we want to decide if we can just drop them or not. Well, let's go back to the differential equation. We had dy dt in this simplified way as 1 over 90 and then 0.05 minus y. And y represented the amount of carbon dioxide, right? Well, carbon dioxide, what is happening to carbon dioxide in this room? So let's remember, we had this room that had this amount of carbon dioxide that was higher, and then we were pumping air in that had less carbon dioxide in it. So it had more to begin with, and then we're pumping in cleaner air essentially. So what's happening is that the amount of carbon dioxide is decreasing. So carbon dioxide is decreasing in that room because we're pumping in fresher air. It's not quite perfectly fresh air, but it's fresher air than there was to begin with. So if the amount of carbon dioxide is decreasing, dy dt must be negative. So 1 over 90, that's positive. So this quantity right here, 0.05 minus y, right? So that implies this 0.05 minus y quantity must be negative. So here we are going to drop the absolute value bars, but we're going to make this negative instead. And that was just because of the context of the problem on this one. So now let's distribute the negative through right here. Negative 0.05 plus y is equal to 0.1 e to the negative t over 90. And then we'll add 0.05 to the other side. So y is 0.05 plus 0.1 e to the negative t over 90. Now let's do our check and see if this matches the initial condition. When we substitute in 0 for t, so if I let t be 0 right here, e to the 0 is 1. So what do I have left? 0.05 plus 1, that's 0.15. And that was how much carbon dioxide there was initially, 0.15. So this checks out as the function that represents how much carbon dioxide there was to begin with. So I'm going to box this in because this is my answer. I didn't necessarily want how much there was in as a percentage at a certain time. Just in general, if we substitute in different times, this will tell us the amount of carbon dioxide there is. Now, there was a follow-up question. It said, in the long run, how much carbon dioxide will there be in the room in the long run? So what we're really being asked to do here is consider the limit as t approaches infinity, right? In the long run would be towards infinity as time goes on. What happens to the amount of carbon dioxide? So what happens to 0.05 plus 0.1, and I'm going to write this in a different way for a reason, 0.1 over e to the t over 90. What happens to this expression? Well, I rewrote this with a negative exponent. I brought it to the bottom. And that's because what I want to see here is that as t goes to infinity, this exponential is going to get huge. So this quantity right here is going to go to 0. And so what's left is 0.05. 0.05 as a percentage. So as time goes on, right, what's going to happen in that room? Well, the room is going to have 0.05% carbon dioxide. And that should make sense. If I think about the original problem, it started with 0.15 percentage of carbon dioxide, and we're pumping in this cleaner air that has a concentration of 0.05. So in the long run, what's going to happen? Well, yeah, it's going to reach that cleaner air of 0.05. It's not going to get any cleaner than that because we're not pumping in like fresh air, but it's going to approach that quality of air that we were pumping in. So that's the answer to the second part, in the long run.